So in this lecture, we will see the complex flow potentials of simple flows, simple flows, such as uniform flow, source, sink, vortex flow, and vortex flow. So, we will see these cases, how to derive the complex flow potentials of these simple flows. And uniform flow. So for uniform flow, let us first consider that a flow. This all these will have okay, some. Okay, this is a uniform flow, right? Uniform flow. I am showing a uniform flow parallel to the x-axis, having magnitude some unit. Okay, like that. So this is a uniform flow. That is all the flow comes parallel to x-axis but perpendicular to y-axis or perpendicular to y-axis. Okay. For deriving the complex flow potential, we must remember this equation of f dash z, which is the complex velocity, which you know that is u minus iv, where u and v are the horizontal and vertical components of velocity. Right? And you can have the other equation also. You must remember that is in terms of the radial component of velocity and tangential component of velocity. Tangential component. This is u theta. So this in the e raised to I theta is equal to ur minus iu theta. So these two equations for the complex velocity, if you remember, you can derive all these things very easily. Complex velocity. This we have seen, the derivation of this we have seen the last one previous class. F dash is equal to u minus I. So for this particular uniform flow, we can easily take this one. F dash is and do the derivation. F dash is equal to u is horizontal component of velocity is u infinity and v is equal to 0. So u is equal to u infinity. So it is like this. So that is it. Then what is F z? F z is integral u infinity dz. It's simple integration. This is the complex flow potential of a uniform flow. So this is the flow which is with the which is parallel to the x-axis, but we can have a flow, uniform flow inclined to the x-axis also. So in that case, suppose you have like this, so an inclined velocity. Okay. So you have x-axis, y-axis. Okay, and right. This is an inclined. So same length, but u infinity, but inclined. So which will have a horizontal component, this component u infinity cos theta, and this vertical component is u infinity sin theta. Okay, let me change this theta to some alpha. So cos alpha. So this is small u and this is small b. So our f dash z now, f dash z is equal to u minus iv, the same equation we use, but this is equal to u infinity cos alpha minus I into u infinity sin alpha. So you take u infinity outside, this is cos alpha minus I sin alpha, u infinity into e raised to minus I alpha. That is f dash z. So what is f z? F z is equal to integral f dash z dz, that is integral u infinity e raised to minus alpha dz, that is equal to u infinity e raised to minus alpha z. So you get e raised to minus alpha z. This is the problem. Now let us come to the source flow. Source. So source, we know that it is like this. So we have on a circle. If you look at in a circle, there is a it consists of radial flow emanating from the origin or center. In this case, we are having the center of the source is at the origin of the coordinate system itself. So flow is emanating here, and they will be flowing radially. This is a circle. This is a circle of radius, say R, and we call the strength of source. The strength of source. M is the total volume rate of flow. Volume rate of flow. Okay. Suppose the radial velocity is UR into the area, this circumference of the circle is 2 pi r into certain height, and the height we take it as 1, the height, which is equal to M. This is how the strength is defined. So likewise, you can write UR is equal to M by 2 pi r. So this is in UR, and tangential velocity is 0. No flow. There is no flow like this. Flow motion in the tangential direction is not there. So this motion is not there. So we can easily write U theta is equal to 0. So the better equation for deriving f z is f dash z into e raised to I theta. You take it as UR minus I U theta. This is in terms of UR and U theta. So this is 0, and instead of UR we can substitute M by 2 pi r. So f dash z now becomes M by 2 pi into r e raised to I theta, and you know r e raised to I theta is z, that is M by 2 pi z. So now f z is M by 2 pi integral 1 by z dz, that is M by 2 pi logarithm of z. This is the complex law potential of a source with its center coinciding with the origin of the coordinate system. Suppose the center of the source is some other point, say some alpha distance along the x direction and beta distance along the y direction, so that this point, if I denote this point A as A is equal to alpha plus I beta, then the source flow will be, the flow will be like this. So the flow will be emanating from this point. So the origin will be shifted to this point, so that we can write f is for a source with center placed at a different point A, an arbitrary different point A as logarithm of z minus A. This is about source. So similarly we can write for the sink. What is the difference is that sink is the flow disappears at that point. So flow comes like this and disappears at this end. So this is what is sink. So the only difference is that the strength becomes minus F. So sink, if there is a sink is there, then F is equal to minus M by 2 pi logarithm of Z minus. This is about a sink. Now we will consider the vortex flow. The vortex law is also it is also the free vortex law. The motion is circular motion, tangential motion. The fluid particles will be circulating or rotating. So the fluid particle is rotating in a vortex law. In a vortex law, the difference is that the fluid particle is rotating. So if I draw a circle, so the motion will be like this. So motion will be along along a circle. So this is at a particular radius r. The strength of vortex law strength is defined as the circulation. Circulation gamma is equal to the line integral of velocity. Line integral of velocity. So line integral, it is moving along a circle. The total line integral becomes the velocity multiplied by total length of the curve. That is 2 pi r. So this is how the strength of a water flow is defined. So we have u theta is equal to gamma by 2 pi r. So this is u theta. So again we will use f dash z into e raised to I theta is equal to ur minus iu theta. But here what is ur? What is ur is equal to 0. So then we will have f dash z e raised to I theta is equal to minus I gamma by 2 pi r, and f dash z is equal to minus I gamma by 2 pi r e raised to I theta. R e raised to I theta becomes z I gamma by 2 pi z, and fz is integral I minus I gamma by 2 pi 1 by z. 1 by z is that is equal to minus I gamma by 2 pi log z. So this is the vortex law. Place the center with the center of the vortex at the origin of the origin. So if it is another point, fz is equal to, so this is about the vortex.